Hello. Okay. Maybe shall we wait for another minute? First of all, let me see whether I can share screen first. I'm sharing this screen. Okay, can you see the share screen? Good. Okay, today we shall continue with the uh, star what? Star evolution. Last time we looked at the small mass star and the medium mass stars. Today we are going to look at the heavier star. So about the massive stars. We talk about lives, uh, the uh, the lifetime they will stay in the main sequence for different masses of star. When the star is heavy, the time they stay in the main sequence is shorter. The smaller the star, the longer it will stay in the main sequence. The whole reason is because for massive star, it is much hotter than the medium to low mass star, and therefore they are recombining into each other much faster, and hence with a larger radioactive pressure, and therefore it will blow away its material much faster than a smaller mass star. So in a massive star, the core is already large enough to enable heating up, and the shell is burning hydrogen. Burning hydrogen meaning hydrogen is recombining to form helium. And as the helium is formed, it is continuously migrate towards the core. So the core is very massive, very high density. It's so large that the electron degeneration pressure doesn't have the chance. So when these stars expands and cool, they will not brighten up like a massive, like a medium star. So the whole thing is we have a very large collection of hydrogen gas. This hydrogen gas is so massive, so it is very very hot. So hot that outer shell is already burning hydrogen. Doesn't like the medium star where the burning is in the core. In massive star, the burning is actually in the shell. As it is burning in the shell, more and more higher, heavier nuclei are formed, and these heavy nuclei migrate towards the center because they are heavier. Lighter elements so as it's burning, the shell is actually expanding and then pushing away, and then more material is pushed away. So it is just like evaporating. It's very quickly evaporating, and therefore it will not like a normal star at the last when it will collapse and then suddenly has a hydrogen helium fresh and very bright. It won't. So the evolution depends again on its mass. When it is about 40 times the mass of our sun, then they will be very bright and very quick. The whole process takes tens of million years instead of like our sun, which takes 10 billion years. So it is several orders of magnitude shorter in their life. And then you will develop into something. We don't really care about all this. What we are interested is understanding that in this very massive star, the core will ignite by itself because it is so large and so heavy. So it's very high temperature. The core of the massive star defined by the lighter elements is in the shell, which is keep on burning, and then as it burns, it become helium, and the helium keep on moving into the core. The core basically refer to the region where there's almost no hydrogen. In this very hot region, it will be able to form carbon, oxygen, and so forth. So for any star heavier than 8 times our sun, then the carbon itself will fuse to form lithium, sodium, and magnesium, and so forth. At the same time, of course, being with such amount of energy, so there are different kinds of elements being formed inside the core, but mainly it will form all the elements before iron, because the elements before ions is exothermal. When it is formed, it will give out energy. For the elements which is after iron, they are endothermic. That means they will absorb energy. But since the core has so much energy, there will be a little amount of all these endothermic elements as well. So there are different kinds of elements there, but mainly it will only form up to iron. When the carbon burning is complete, then they already will, because as I said, because it's so hot, so the material is being pushed away very, very quickly. By the time they finish burning carbon, it's already 2.5 times the mass of like our sun. So it is losing its mass very fast. This process become unstable, and then it will create a supernova. A supernova. Let me skip this part. A supernova is when the core of a massive star collapses. It will form a neutron star. No more positive charge. It will become a neutron star. And if it is heavier than a certain limit, it will become a black hole. So we don't really care about all this. What is important is the last sentence there. Because some of the unbound material is bombarded by neutrons, some of its nuclei captured, then creating a spectrum of heavier than iron material, including radioactive elements up to uranium. Because at the last stage, there are so much neutrons. Neutron is bombarding everything and creating all sorts of radioactive elements beyond iron. So let's forget about all this. They are just what I want to concentrate is actually this graph. Okay. This is the so-called binding energy nuclear particle curve. Now, what is this graph means? Okay, horizontally is the number A. Basically, it should be, I think it should be Z, not A. Sorry, it should be mass number A. But we have to remember mass and okay, sorry. Let me go to this graph first. In this graph, the horizontal is Z. Z means number of protons. The vertical is the number of neutrons. So for all those nuclei, which is stable, is denoted by black on the line. So, for example, this is a stable nuclei, stable nuclei, stable nuclei, stable nuclei, etc., etc. So all these stable nuclei is black. And this is Z equal N. The number of neutrons and number of protons are equal. So for example, carbon will be somewhere here. This is 20, this is 10, and carbon will be something around here. So this one is probably a carbon. Carbon has 6 protons, 6 neutrons. So going to that side is also somewhere here. So that is a stable carbon nucleus. But carbon also have carbon 13. So there's another carbon which is also stable, but not too stable, because carbon 13 will eventually will decay. But anyway, so this is all the lone elements stable nuclei. And on the other two sides represent how fast it will decay and then will become a more stable. So this is the stability curve, so to speak, of all the known nuclei, all the elements, different elements. Some of them you will notice there's no black area. These are no black. That means they are not stable. Some of them will have much longer lifetime, like this one is 10 to the power 24. So it is quite stable, but still not exactly stable. But some other here, down right there, it exists only for 10 to the power minus 8 seconds. So it is just very quickly disappear, very unstable. So there are a range of stable and unstable elements. Some of them, for example, will have a half-life of about 1 second. That means if there are two nuclei, then in 1 second, one of them will gone. So that is the curve here. Now this is the so-called stable nuclei curve. Now going back to this picture now. This is the mass. And these are the red line here represent the stable nuclei. Only the stable nuclei elements are in this red line. The vertical is so-called binding energy. Now, what is binding energy? Binding energy, let me see, okay. The binding energy is nuclei. We know that in the nuclei, we have neutrons and protons. Protons are both positive, and therefore they repel each other. So we need something to hold them together. That something holding them together is called the nuclear binding energy or strong force. The strong force exists between protons, neutrons, and neutrons, and protons. All proton neutrons both have this strong energy, but the electrostatic repulsion force between proton is greater than its binding energy, so it cannot stick together. So we cannot have two protons by itself. But if we add a neutron there, the neutron's binding energy will be able to hold them together. So we have helium-3. Helium-3 is two protons and one neutron. The stable helium is helium-4, two neutrons, two protons. So they will bind together in the middle. Now, each individual proton will have a mass. Each individual neutrons will have a mass. When they combine together, we would expect them to have the mass of one neutron plus one proton. But no, they are slightly have a slightly less energy, a less mass, is slightly lighter. Why? Well, it's because when you bind them together, it is energy. The energy, according to Einstein's equation, is the same as mass. E equal to mc squared. C is the velocity of light. So the energy which is binding them together is taken up from the mass of these two nucleons. So a proton lost a little bit of mass and neutron lost a bit of mass. This loss of mass becomes a binding energy. And therefore, we can measure the binding energy of nuclei by weighting the nuclei. For example, we have nuclei of two neutrons, two protons. So we know the weight of two neutrons, the weight of two protons. Add together, we know how heavy it should be. Then we measure the mass of a helium nuclei, helium-4 nuclei, and find that after dividing the mass of the nuclei is less than the four of them add together. So we take the difference and then divide it by 4 to get to this curve. So this is not a lot of binding energy per nuclei. As the nuclei getting bigger and bigger, more and more nuclear there, so that there are more and more energy within them, and therefore its binding energy increase. Its binding energy increase until reaching iron. Beyond iron, then the binding energy started to decrease. We can think of it like this. We have something which repel each other. We add something in to stick them together. That something sticking them together is the energy. The more you stick together, the tighter it's become. The more you add the neutron there, the higher the sticking pressure, and therefore it's collapsing, squeezing itself. Up to a certain point, you want to squeeze it more, then you will start it, don't like it, you want to split apart. So looking at this curve, we can understand that for elements in this region, in the top horizontal region, then when you, for example, we have an element somewhere here, uranium. When we split it into two different fragments, so it will split, say, from about 230 something, 38 to 235. We split it, it will become 120 something. So 120 something. We split it to somewhere here. So when we split it, some of the energy which is squeezing them together is released. So this is the energy which is released in between this. And this becomes the energy in nuclear reactor. So the nuclear reactor makes use of this part for nuclear fusion. Now, in order to trigger nuclear fusion, we have to use this curve. For uranium, so it is around 90 something here. Uranium 238 is somewhere here. Probably one of those little dot there is a uranium. In this uranium, it is stable at that point, but if we try to inject a neutron into it, so we add its mass, then it will move upwards. We inject a neutron, then it will move upwards. Then it will become unstable. Some of the black dot upward is not black, so it will be unstable. Unstable, then it will split. So there are two ways of splitting a nucleus. One is by bombarding it with a neutron. So basically, we have a very heavy neutron here. It is squeezing itself too much. It wants to break apart so that it becomes less squeezing. Then we use a neutron hit on it. When the neutron hit on it, it absorbs the neutron. Then it becomes even squeezing itself so hard. Then you find it is better to split. They will split up, and during the split up process, release energy. So that's one way. Now, during that release, we notice that the N and Z is not exactly on the same line. So in here, there are actually more neutrons than protons in this region. But as it moves down, the ratio becomes a little bit different. So the neutron and proton becomes closer together. So there are excess neutron, and this excess neutron will come out. So how the energy released? The energy is released by two methods. The nucleus itself, kinetic energy, and the neutrons, kinetic energy. Both of this energy is heat, and therefore when we do a fission, then the nucleus split up and becomes moving very fast. This is heat, and the heat you have to be absorbed by something to drive the turbine or drive the engine. When we are splitting it, normally we use a stable nuclei, so it won't split. It's stable. Black is stable, so it will take millions of years before it will decay. It's very stable. The trigger for it stable is the neutron. So we want to inject a neutron into a heavy nucleus to cause it to split. That neutron control the rate of reaction. Normally, when it splits, it will eject about 3 neutrons. So if you let that go, so one neutron hit on one, and then you will produce 3 neutrons. That 3 neutrons will hit on another 3 nuclei and form 9 neutrons, and that 9 neutrons will hit on another 9 nuclei and form 27 neutrons, etc. So it will quickly, very quickly, release too much energy, and that is the nuclear bomb. The nuclear bomb, because you do not control the amount of next generation neutrons. So as soon as you have one neutron hit on it, then the neutrons will trigger another 3 neutrons. The 3 neutrons trigger another 3 nuclei to split, causing output of 9 neutrons and so forth. So it have a runaway explosion. So that is for a commercial use of nuclear energy. We need to control so that the number of neutrons is maintained at a constant. So 1 neutrons coming in, hit on 1 nuclei, it will produce 3, but we will try to absorb 2 of them or remove 2 of them so that there's only 1 remaining to continue the reaction. So how do you maintain that one? Well, one is by losing it to the environment. So suppose I have a lump of uranium here. So a neutron somehow hit it onto the uranium lump. There's a lump, a large number of neutrons here. So that one of them split, it will eject 3 neutrons. But if 2 of them get split in the other direction, escape from here, then that 2 neutrons will not trigger any more reactions. Only 1 will continue inside. So if one of them continue inside, it will split, and then you will eject 3 in early direction. But if that 3 is not kept, 2 of them is not captured, have left the core, then it will not have an explosion. So in order to have a nuclear explosion, we must make sure that all the neutrons produced at the beginning will be captured by some other neutrons, some other nuclei, in order to trigger the next generation, and then it will need to trigger the next generation. Therefore, we need it to be of a certain size. If it's too small, then your neutron hit onto it, the escaped neutrons will go to the surrounding and not causing the next generation reaction. But if it's large enough, then a neutron hit on it, the neutron generated from this will be able to capture by surrounding nuclei and then causing the next generation of reactions. So in order to trigger a nuclear reactions, we need two things. One is it has to be have a critical mass, certain size. If it's too small, it won't explode. If it's too large, it's larger than a critical mass, then it will have explosion. So the way to do it is we have 2 smaller lumps, separate out at the beginning so it is safe. When it's time for nuclear reactions to occur, nuclear explosion to occur, we lump them together so that they becomes a larger mass beyond the critical mass, then it will explode. So that's one way. In order to control that, in a nuclear reactor, on the other hand, we space out all the uranium, so that the uranium is not all mixed in one concentrated area, but rather will be spaced out in nuclear rods. So that's one way. And in between the nuclear rods, we use something to absorb the neutrons. One of the good absorption is carbon or another good absorption is water. So we use water both as a coolant as well as a neutron absorber. So in a nuclear reactor, then all the nuclear are in rod shape, and then they are slide into the nuclear reactor as fuel rods. In between them, there are the modulator, the water, and some elements which will absorb neutrons. When it is shut down, the absorptions material go in between all these rods, absorb all the neutrons, so that there's no reactions. But when it is necessary, you just pull out the moderator rods, the natural neutrons started reacting, and then you will continue. The trick is to maintain the average number of next generation neutrons number is the same as the last generation, and keep the reactor at a constant speed, constant voltage, constant output of energy. Okay, back to this graph here. On this side, we notice that it is splitting. When you split it, then it will move from this region to this region, and hence releasing the bonding energy. And therefore, we have an energy source. On the other side of this curve, if we move from a high energy to a small energy, it will absorb energy in order to bind them together. So there's you cannot split the element on this side to produce energy, but we can produce energy by combining them together. So on this side is the fusion. We need them to stick together. The difficulty of fusion is the nucleus and nucleus are both positive. For a neutral atom, the nucleus is positive, but there's an electron cloud around it, making it looks like neutral. So we have neutral atom and neutral atom spacing like that. For the nucleus, they are too far away. They will not attract each other. The strong force is a very short distance force. So it is too far away. We cannot get them to combine together. So the first thing is we need to remove the electron outside. So we have the nucleus. There's another nucleus. Say this is a proton, this is a proton. The two protons, we need to bring them together. As we bring them together, the electrostatic force is repelling because they are both positive. So what we need to do is try to get them close together by running very quickly. So they are running very quickly towards each other. The faster they run, the more energy it is, so the closer they can be. If it is close enough, then you will fuse. So the critical thing is how quickly they are running towards each other. How quickly it's running towards each other depends on its temperature. When its temperature is high enough, then it has the chance of hitting each other at a short distance so that they can fuse. So what we are doing on Earth today about the fusion reactor is to try to maintain a very high temperature. The temperature needed is about 10 million degrees. Sometimes maybe 1 million degrees will do, but the current target is going to 10 million degrees. So the question is, how can we maintain 10 million degrees and holding all this together without escaping? Most of our material, the melting point is around several thousand degrees. 3,000 degrees is almost the maximum temperature at which something doesn't melt. So if we are going to hold the nucleus at 1 million degrees, it is several order of magnitudes higher than the temperature of the melting point of the container. The container, no matter what material make of it, the melting point is a couple of thousand degrees. So the way to hold the high temperature nucleus together is by magnetic bottle. The idea is that we have a very strong magnetic field. Now we know that when a charge moves through a magnetic field, it will generate a force perpendicular to it. This is the theory of making an electric motor. So when the charge is moving around a very high magnetic field, it will tend to turn. So by rotating the nucleus within a magnetic field, we can hold them together. So usually it is done by using a circle, a toroid. So the nucleus will be rotating and moving around the toroid inside a very strong magnetic field. The magnetic field hold the nucleus together. So in order to do a fusion reactor, the first thing you need to do is produce this high energy nucleus. Inject them into a magnetic field so that they will move around a magnetic field. And then as they move around a magnetic field, we add more energy to it so that it becomes hotter and hotter until it will be so hot that they can hit on each other and generate energy by themselves. And then we will need to figure out how to extract the energy out for generating of electricity. So there are a number of different difficult problems to solve at the moment. For fusion, at the moment, the best example is have been done in China. They can hold a 10 million degrees plasma, the thing, for about 100 seconds. But that's not long enough. We need them to hold the plasma at infinite time. We cannot just allow it to run for 100 seconds and then you shut down and then you have to inject all the energy in to get it working again, and then you will just work for 100 seconds, you stop. It doesn't work. We need to continuously maintain at a 10 million degrees in order to have a continuous fusion. But anyway, now we understand that all these different elements are formed from stars. The question next is, how is our solar system formed and why we have so many different elements already next to us? Well, the answer is, when our solar systems first started, it was started by a supernova, by a massive star which exploded. When the massive star explodes, it will send out a shock wave, and that shock wave trigger our sun to start burning. But because the supernova, when it explodes, all its material is sent all around the neighborhood, and therefore our sun is able to capture some of these heavy elements. So when we look at our solar system, the sun is mainly hydrogen, and surrounding the hydrogen there are a few heavier planets, including us, Earth. But beyond Earth, then the planets become lighter and lighter. The outer planets are basically water, and some of them are just hydrogen. So that is the implication of all this. So far from our cosmology, we understand that our universe started as a very tiny bit. It expands. At certain time, around 400,000 years, then it becomes transparent. We have an image of that one, the microwave cosmic microwave background radiation, and then it will be dark for quite some time until some stars started to burn. When the stars started to burn, it will give out light. During that process, the heavier stars will burn faster, and therefore it will explode earlier, and that explosion trigger the second generation stars to burn, and then here comes our solar system. So far up to now, we understand how the universe come from a very simple beginning with almost no structure, and then a little bit of random noise. The difference in temperature shown is in the cosmic background radiation. From that little differences, it becomes galaxies and stars, and galaxy and stars produce all the other elements that becomes known to us. Any question? Let me turn everybody's sound on, and I can stop the screen sharing. Okay, unmute all. Okay, anyone like to have any comments or question? No? I can't hear you, Gilbert. Yeah. No, maybe I should put on my headphones. Let me try it. Where's my headphones? Okay, I'll try to put on my headphones, see whether I can hear you. At the moment, I can't. Okay. Can you hear me now? Yeah, you can hear me, but I can't hear anybody. No sound coming from anybody. Let me check my sound. No, I am having my headphones. Let me check the input. Where's my sound input? Input is here. Output headphones. Yeah, but I can't hear you. No, I can't hear. No, there's no sound coming from anyone of you. Can you check your sound setting on the lower left hand corner? I see Sam signal iPad is having a, yeah, I see some of your audio signal coming up, but I can't hear anyone. And looking at my sound system, should be correct. Yeah, it should be correct. Let me see whether there's another thing blocking the sound. What's that? This one. No problem. No problem. Where is? No, I don't know which one is blocking you. I can't hear you. Sorry about that. Is that coming from here? Problem? Where is? No, I don't know which one is blocking you. I can't hear you. Sorry about that. Now I can hear you, but I doubtful whether you will have an echo. Is that coming from here? No, I can't hear anyone. Can't hear. Where is? Maybe no, I don't know which one is blocking you. Maybe you can type in as. Now I can hear you, but I doubtful whether you will have an echo. Is that coming from here? No, I can't hear anyone. Maybe you can type in as can hear a chat comment so that I can maybe. So I don't know which one is blocking you. Maybe you can type in as. Now try to type in as a chat. Now you can ask me questions through the chat, please. No? Well, that's a problem because the next session, China Today, we are going to have a discussion. If I can't hear what you say or other people hear what you say, then we can't have a discussion. Yeah, I can't hear you. I don't know what you're saying. So if that's the case, I might have to call off the China Today. But anyway, well, in that case, I think we'll end this one first, and then check out. Use the rest of the time to check out in the China Today session, and make sure that we can hear each other. Shall we end this now? Okay. Okay. Bye bye. We'll end this one and start the other one.